Hello, this is Lab 4 for Physics 2211. The purpose of this lab is to observe the oscillation of a spring with a mass attached to its end. The physics principles used in this lab include Newton's second law and Hooke's law for the spring force. As you can see, the gravitational force is equal to mass times gravity, whereas the spring force is equivalent to the negative spring constant, K, times s squared, or L minus L initial times L hat. The net overall force is the combination of these two. And finally, velocity equals the initial velocity plus this net force over the mass times the change in time. And the final position is R initial plus V delta T. We also use the energy principle in this lab. For this, kinetic energy is 1/2 mass times the velocity squared. The potential gravitational energy is the mass times gravity times the height, and the potential energy from the spring is 1/2 times the spring constant times s squared. The total energy in the system is all three of these put together. The initial data in this experiment include the mass's initial position, its initial velocity of 0 meters per second, its mass of 0.402 grams, and the length of the stretched spring at rest, L, which is 0.7 meters. After entering the information into Tracker, here's what I got. From its initial position from rest, L is 0.7 meters, as explained before, and the y-axis was lined up with the spring at rest, which needed to be tilted just slightly. Based on the data from Tracker, multiple values were calculated. The first was t, the period of oscillation, calculated by taking the average of the t-values between each consecutive trough of the graph. Using this value, k, the spring's constant was calculated to be 6.824 newtons per meter, leading to the value to the force of the spring as well. Next, I calculated the gravitational force, and after setting these two values equal to each other, L initial, or the relaxed length of just the spring, was determined to be 0.12269 meters. After these calculations, I went to VPython to enter the data to model the motion of the spring with the mass attached. Here is the while loop of my code. First, I entered in the data for the gravitational force, which is negative mass of the ball times gravity, the force of the spring, which is the negative spring constant times L hat times S, the net force, which is these two values combined, the ball's final velocity, which is its initial velocity plus the net force over the ball's mass times the change in time, and the ball's final position, which is its initial position plus the ball's velocity times the change in time. L is calculated to be the position, the ball's position minus the spring position, and L hat is this value L divided by the magnitude of L, and S equals the magnitude of L minus L initial. And finally, the kinetic energy was entered to be 1/2 times the mass times velocity squared. Its gravitational potential energy is the mass times gravity times height. And the spring potential energy is 1/2 times the spring constant times s squared. Now, if I run the code, we can see the computational model of the spring's motion with the mass attached to it. The blue ball represents the modeled mass, and the red ball represents the actual mass based on data from Tracker. The blue arrow in this model represents the spring force, and the black arrow represents the gravitational force acting on the mass. The predicted and observed motion are very similar. Here are the two graphs generated by the VPython code. The first is the graph of the observed versus predicted motion, and the second is the graph of all the energies acting on the mass as it moves. As you can see, the kinetic and potential energies oscillate as the mass moves, but its total energy, represented by the yellow line, remains at 0 throughout the period that it is moving. So what does this all mean? Is the energy principle satisfied? Yes. This is because all the energies, which add up to the total energy, equals 0. And as I stated earlier, this is represented by the yellow line, which stays at 0. Now to estimate the oscillation periods. Based on the data I obtained in Tracker, I found the average t-value from the y position data to be 1.525 seconds when using the most accurate data I obtained. And based on the same data, I found the average t-value from the x-position data to be 1.638 seconds. The reason for the differences between these two oscillation periods could possibly be the effect of the Earth on the mass in the y direction. The y-position data is more accurate than the x-position data because it is affected by both the gravitational weight force and the spring force, while the x-position data isn't affected by all of the separate forces until the end of the cycle. Well, that wraps up my Lab 4, and thank you for watching.